Hello and welcome to our Design Lab 2 production video. Today, we will be discussing and implementing new ideas into our production line of tape measures. In this video, we are going over the entire process of finding an efficient production line. This includes getting familiar with the product itself, concerns we have about building it, our first run of Lab 1, problems we found with it, new solutions, another run with set implemented solutions, and finally comparing our results with the first run. The tape measure consists of 6 parts: the casing, which has a front and a back, a pre-assembled component, which is the tape, casing, and spring, a black stopper, a white bottom guard, 3 screws, and a belt clip. Our primary concern for our first run is the variability of the pre-assembled component and the time it takes to assemble it. This station thus has the largest time variation and is prone to cause delays.
After our first run of Lab 1, we had observed several problems during the building of the measuring tape. First, we spent a considerable amount of time removing tape on the core of the measuring tape at the first workstation. Second, when picking up the white bottom guard, it was not easy to determine which end was the front or the rear when trying to fit into the case. Even when having the 3 types of screws separated into their own bins, we still spent time trying to find the right screw and orientation when picking up. Separating the job of screwing in the screws was not efficiency as they could all be done under the same station within the takt time. For our solution, we recommend using a medium string glue or tape between a rolling measuring tape instead of tape wrapping around it. We can create the special bin for the white bottom guard that will feed the operator the correct side. Screw will be placed in sponge-like holder for easier removal and in the correct orientation.
We can see that our second lab with the implemented solutions had considerably decreased our time from 2 minutes and 17 seconds to 1 minute and 28 seconds. In order for us to have done this, we found that it was important to redesign and re-engineer our production line using the just-in-time system. The reason that we had chosen JIT was that so we could decrease the variance in each station. The way we currently had it set up did not allow for the correct orientation of pieces when picked up and would have workers spend various amounts of time to properly line up the parts into the product. This was an important aspect that we felt we had to fix. Our first solution implemented allowed for easier installation of the tape into the case without the need of having to remove an outside layer of the tape, thus preventing the core tape from being released. Because of this, the only step needed in the first station was to wind up the tape into the casing and allowed for the task to be done at a near identical time. The inside tape would then easily be removed at the end of the product line. The solution of having the screws held up and labeled by sponges allowed for the worker to pick up the screws in the correct orientation and place them correctly into their slots for screwing at the next station. This decreases the variance as no time is needed to correct the ways the screws are picked up from the original bin. Most screws picked up with this method average around the same time to be placed into their slots. Having a feeder system for the white bottom guard allows for the worker to select the part without needing to worry about its orientation. This allows them to easily insert it into the casing with little to no error.
By applying various manufacturing concepts and programs to our assembly process, it was our goal to reduce the takt time and variance of our operation. In order to meet customer demand, we were responsible for designing an assembly line that was able to produce one measuring tape every 24 seconds. We conducted 30 trials on our first method and determined the mean cycle time to be 33.4 seconds. The main reason our takt time was so high is we failed to include the time that it took the worker at workstation 1 to first remove the tape on the exterior of the coil spring. Our solution to this problem was to attach a small adhesive to the inside of the tape measure. This allowed the worker at workstation 1 to immediately start attaching the coil spring to the housing unit. The worker at the final workstation would be responsible for removing the small adhesive at the end of the process. The replacement of screwdrivers with power drills drastically decreased screwing time, allowing us to only need 3 workstations. After implementing these changes, we conducted 30 more trials and found the new average cycle time to be 23.67 seconds. To truly know if we were successful in reducing cycle time, we conducted a comparison of means. Sample means and sample standard deviations are shown on the slides. Solving for t, we get a value of 2.39, and our critical value is approximately 1.671. Because our test statistic is greater than our critical value, we reject the null hypothesis that the two mean cycle times are equal, and conclude that the mean cycle time of method 2 is significantly less than the mean cycle time of method 1. Variability in manufacturing systems can lead to many operational inefficiencies such as longer cycle time, lower throughput, and higher work in progress. Theories of operational management such as just-in-time, JIT, suggest many ways in which the variance can be reduced. Using better equipment and tools and investing in worker training are just a few of the ways. In our assembly process, we replaced screwdrivers in all workstations with power drills. We designed a mechanism that aligned the white stoppers, allowing the worker to pick up and place easily. To prove that we were successful in reducing the variance of the assembly process, we compared the variance of both method 1 and 2. The sample mean and standard deviations of both methods are shown. We find the test statistic to be 3.296 and our critical value to be approximately 1.64. Because our test statistic is greater than our critical value, we reject the null hypothesis that the variances are equal and conclude that the average variance of method 2 is significantly less than the average variance of method 1.
An idea that we wanted to implement, but couldn't due to lack of resources and time, was to include a power drill. The use of a power drill allows us to remove a worker and save money on wages. It is shown in our cost analysis that an average drill will cause an increase in the cost for tools. However, it will drastically lower the wages cost and will produce much more units while at it. We see that the tool averages an increase in the net income by $25,000. Whether or not less tapes are needed, we see that the drill helps with our procedure if ever needed in the future. That's all for this video, and thank you very much for watching.